So now that we've extended our minimal language with futures and asynchronous function calls, and we define the semantics for such constructs, let us define a type system that matches this new construct. So a type fit system that encodes futures and check correct typing of futures. So before doing that, what I first need to do is recall the previous type system we had in our previous semantics, that is without futures but with functions. So what we used to do is that from variable declarations, we could infer a typing environment that is a mapping from variable to base types. And this was done by a judgment that was denoted ROD. So this judgment was taking a set of variable declarations and producing a mapping gamma. Similarly, from a set of function declarations, we could infer a function table that is a typing environment gamma f, which is a mapping from function name to function signatures. So it would map for each function name declared in my program a signature that can be used to type the call to the function. And this was done with the type judgment OF, which was taking as input the set of function declarations. Then we have a typing judgment for expression that is of the form gamma E tau, where tau is a base type. And we have a typing of statement of the form gamma F S. And here you see we don't have a type for statement, we just check whether a statement is correctly typed or not. The most important rules of the type system I called before. The first line is for expressions, E. It explains how to type operators, like for example you have plus here that should take two integers and return an integer, so check the correct typing of each of the sub-expressions and give a type for the composition of the sub-expressions. For variables, you would simply fetch the variable inside the mapping, so inside the typing environment. And as you can imagine, you have more typing rules for different operators, including Boolean operators. Then for statement, we have those four next main rules. If you want to type, to prove the correct typing of a sequence, you would check the correct typing of each of the two statements. If you want to check the correct typing of an assignment statement, then what you would do is that you would check that the type of the variable, which is denoted tau here, so it is in fact the value gamma of x, because it will use the rule that is written above here. So, and we check whether the type of the variable is equal to the type of the expression we assigned to the variable. Recall here we don't have subtyping or any compatibility checks between type. I mean, compatibility check is just type equality. From that, you can build the typing of other statements like the conditional. So to check that an if statement is well typed, to just check that the expression that is given as a conditional is indeed of type Boolean, and that each of the statements inside the if is correctly typed. Boolean, while is similar, you just check the correct typing of the expression given to the while, so it's a conditional, so it should be of type Boolean, and then you check the correct typing of the statement. Then when we switch to function and function calls and function declaration and whole program, the typing rules are a bit heavier. They are not much complicated, but they involve much more variables and things to be checked. So to type a program, we do this big inference rule. So it starts from a program. Remember, a program has this shape. And from this program, you have global declaration. So here I recall the type system with global variable because that's what we used to have. And we had, this is dm is variable declarations for the main body. S is the main body. And here you have fundef, which is a set of function definitions. So what you would do is that you will first infer a global typing environment, gamma G, from the global variable declaration D. Then you would infer a function map from the function definitions. So now you have the signature of each function and the global environment. Then what you will do is that you will go through all the function definitions. So a function definition has a stage as this shape with gamma the return type. You can see the parameters here, and you can see the body of the function here, dfsf, which df the declarations, and each function returns something, and it's the expression e. And basically what you would do is that you would check that what is returned is of the good return type, that the statement inside the body of the function is correctly typed, and you would check that inside the typing environment that contains the functions if necessary, but mostly contains the variable, and the variables are the global and the local variables. And which are the local variables? It's the one declared plus the parameters. The operator between gamma G and gamma L is a merge that overrides variable declarations. So this allows you to override variables, so you put local variables over the global variables and hide them. Last thing you need to do to type your program is to type the main body, and the main body is S, and you will type it in a setting where the local typing environment is gamma M, which is inferred from the dm, the variable declarations for the main. Then you can type the function call. The function call is typed as follows. You fetch the signature of the called function. So here it's a call to a function f, and the result is put in the variable x. So you find the signature of the function f in gamma f. Then you will check that each of the parameter given to the function is of the right type, to I. And finally, you will check that the return type of the function to is the type that you put in the variable x. So now let's quickly get into features. So previously in the type syntax, we used to have integers or boolean. And now we want to extend it with features. So we want to have integer, boolean, and features. But we don't just want to identify features. We want to know which is the type of the value that is stored in the future. Because typically when you do get of f, you want to know whether you will obtain an integer or a boolean or another feature. So the type syntax for features is now integer and boolean as before, or fut of 2. So you see, you can have future of integer, future of boolean, but also future of integer or of boolean, and so on and so forth, whatever finite structure that contains futures. So it's a type system that looks like parameterized type that you can find in classical languages, and that's how you would define parameterized type in this setting. So now you can declare future types. So in the variable declaration, you can, for example, have future of int x, y, which means x and y are two variables that will contain future of integers. And we'll check structural type equivalence, which is a big name for just saying that we'll check that the structure of the types is the same. So to match a future of integer, you need a future of integer. Okay, so now we can type the two constructs for future, which is, remember, asynchronous function calls and get. So what an asynchronous function calls does is it does exactly like a function calls, but it does it in another task, and it doesn't just return the return value, it returns a future that will contain the return value. So that's what we will do here. So Here, if you have a look at the previous slide here and compare the old rule with the new one, so the old rule, remember, it was fetching the future, checking the parameters, and checking the return type with x. And now we do the same. We fetch the function signature, we check the correct type of each parameters exactly as before, and now we infer that the x must be of the good return type, but the return type is not simply to as before, it's future of to, because x will contain a future that will be filled by something of type to. And x, you don't choose it as it is, you use it because you use it inside a get. And the typing rule for get is to correctly type a get statement with an expression e. I should check that the expression e must be of type future, so I cannot get something that is not of type future. And this future must contain another type to, and this type to must be exactly the type of x. So what the get will do is that it will open one of the future type. It will unroll the future container and get the type that is inside. Indeed, you can imagine the future operations as boxing the value inside the container and the get operation as opening the container. So now you can use this type system to type this example. I suggest not to type the f function because it doesn't have anything to do with futures, and just try to type the main body, that is these three statements. But you will need to type it in the correct typing environment. As usual, you should probably interrupt this video and try to do it, and then I will show you how I would do it myself.
Okay, so now let's try to type the example program. To type a program, as if you check the rules, you would check the rule program, and
I'll give informal statements for the moment, and I'll get more formal when we will be typing the body of the main. So you first
fill the gamma and the gamma f. You will check functions and you will check the main. And as we said that we don't want to check the function, so we suppose that this is we don't do that. So what interests us is the setting where you have a gamma g. There's no global variable here, so it's simple, plus gamma of the main, the environment, the function map, and you want to check whether S is well typed, and S is the S of the main, which is this. So what you want to know is what is gamma M, and gamma M looks like this. And you want to know gamma F, which just has a single function, which is F. So to type this, you will type the sequence, which consists of typing each of the element. So, and the second part should also be a sequence because you have three things. And to type this is interesting because it's one of the new rules we introduced. And we check the type of f, which is int to int, and we need then to check that in gamma m3 is of type int. Sounds good. And also in gamma m, t is of type put int, which is also true. I'll just separate things a bit here. Now I can go to the sequence, and the left part is already known. It's about typing function. It looks really similar to the typing of async, so I will just skip it to fit inside my slide and to take not too much time. And the right part, which is a bit more interesting, and it should check the get types, the typing of the get statement. And typing of the get statement, if you look carefully, so you should have your typing rules, of course, at hand. It says in gamma m, I should type t of type fut of int, which is good because that's what we have in the environment. And I should also type x int. In fact, if you look carefully, it's not exactly this. It should be that of type 2 and that 2 for some 2. And a 2 that works well is int, but it could be something else, of course. So here we did a bit of unification on the fly. So yes, the program is well typed, and this concludes this assertion.
Now you can have a look at this more complex example. The syntax is slightly different. It's a bit more of a C-like syntax. But mostly what's interesting to see here is how we can play with the future types. And I suggest you to have a look at this. I will not give a tablet correction. I prefer if we discuss this during the course. But I suggest you first to have a look at each statement and each expression in this program and try to see what would be the good type for each of the expressions and check whether it's correct. Now that we've seen the semantics and the typing, we didn't relate them, and that's what we will do, at least partially next. I will illustrate the properties of type system, and we will focus on one property, which is type preservation. And we will mostly give the principles and explain how we could prove it. Preservation says, considering a well-typed program and the configuration reachable by executing the program, the point is to show that if the configuration is well-typed and we do one step of reduction, then the configuration after one step of reduction is still well-typed. So as we will start hopefully from a well-typed configuration, we'll prove that the configuration is well typed all along the execution, and this will allow us to prove that the properties ensured by our type system, like for example, I always do a get and a future, will be true all along the execution of the program, whatever the execution is. So that's one of the basic notions you have for typing. And the other one, as you can remember, is well-typed program cannot go wrong. We won't illustrate any well-typed program cannot go wrong property in this course, but for example, as I said, you could use it to prove that when you do a get, it's necessarily on something that's the future. So let's go a bit more into the technical stuff. As I said, preservation is consider a well-typed program, a configuration that is produced by this program so that is reachable by executing the program. The point is to prove that if a step of reduction is possible from this configuration Cn, and Cn was well typed, then after the reduction, Cn prime is still well typed. What is the right environment for proving that? Here I used a couple of two things, which is gamma f and gamma fut. Gamma f is, as you could imagine, the set of typing of functions, and gamma fut is information on typing on futures. So that's new and can evolve, you see, during the reduction. Anyway, to prove preservation, the first thing you need to wonder is what is a well-typed configuration. Indeed, up to now, we defined what is a well-typed program, what is a well-typed statement, what is a well-typed expression, but we didn't give the type system for programs at runtime, which is configurations. We used to do that a while ago for the first version of the mini-while language. The first version that we had for the mini-while language was this one. It was saying configuration, which at this point was only statement and store, is well typed in an environment gamma if the statement can be typed in gamma. And I don't know if you remember this notion, the store and gamma agree on typing, which is if in the store the value of x has a type 2, so if it's 3 it's integer, then the type of x in the typing environment gamma must be the same. So this gives us a first hint on how we want to do that, but we didn't focus yet on what would be typing for future. So we have two problems. One is to find gamma foot, and the other is to type those new configurations that are different now, which look like this. Gamma foot will not be that difficult to define. It's just a type of each future, and there's plenty of way to do that. But for the moment, let's just put this aside and say that we managed to have a mapping from future identifier to types, and we can maintain it all along the reduction because, for example, each time we launch a new asynchronous function call, we can just remember inside this the return type for the function call and map to the newly created future. That would work, and we'll just need to ensure that when we put finally a value inside this future, it has the right type, which will be ensured by the typing of the return statement. Okay, so that's for this. But now we also have functions, and we have new kind of stores. So everything is a bit more complicated. So our configurations are sets of that kind of things, remember? CTX is of the form, it's couple of sigma s, and it might finish by return e. In fact, it has no return e if it's for the main task, but okay, that's just a detail. So we could almost say that it has a return e on it. Here is the first attempt that is not that far from what we could do. So we can first suppose that for typing S sigma, it's as before. Now we have a gamma f that allows you to type S, the function calls inside S, but it's just the function definition, so we can add it to every rule we used to have for typing configuration. It's simple. So we could suppose that we have the old definition of well-typed configuration, and we apply it to S and the new version of small sigma, which is store composed with big sigma. So that will give us the same guarantee as before. The problem is that for the moment, gamma is undefined. If you try to type configuration, we had this kind of setting where gamma is not known. We just have typing for functions, for futures, and the current statement. But okay, let's suppose we have to write gamma magically and go further. Then we want to type each of the elements of the context, because when you will unstack, you want to show that you want to be sure that the functions that were the function calls that were stacked below you are still well typed. So for each of these sigma s, you want to have the same thing. Okay, it's sigma esi. This should have been sigma 0 s0. So we have this for each of the elements of the context, and we can finally check that the expression returned at the end of the asynchronous function call corresponds to the type of the future, which is gamma foot of f. So we also this way make sure that the typing in gamma foot is agrees with the return types of each task. Okay, so that's for this kind of things. For the futures, it's way simpler because you must just check that the value that is stored inside the future fits with the type of the future, and then you can compose this species of configuration trivially by just checking each part. The problem here is that gamma is undefined. Here I suggest that we don't do it formally, at least not right now in the course, and depending on the time we have during the session, we will unroll a bit that, and if we don't have time, then at least you will have the intuition. Gamma is the environment that types the considered statement. So if you look at this here, it's the local variables of the function that contains the statement s. Problem is that we don't know what this function is. And there are several ways to define it properly. What I find the simplest is to annotate the necessary parts of the configuration with the function that is currently evaluated. So for example, you could say, okay, here I remember that this is inside function f, and I remember that this statement is inside function f prime, and so on and so forth. So you could annotate each statement at the highest level by the function to which it belongs. And I don't know if you remember, but if you have a look at how we were typing things, when we had the function, we could quite simply type the statement of the function. We just need to recover the local variables and the parameters, but that they are known. They were here at the beginning. They can just be stored somewhere or recovered by the right function. Okay, so now suppose you have that. Suppose you can recover the right gamma. The question I ask you is how to prove that small step semantics preserves well-typed configuration. How would you handle such a proof? And that I suggest that we discuss it together during the course. It's interesting to have interaction on that and perhaps to see how far we can go depending on the time we have. Okay, so we've seen a bit how to prove preservation, even if it was not in a fully formalized way, which would have been probably too long or too perhaps a bit boring. So overall, now we have seen an overview of concepts for parallelism in programming languages and semantics of parallelism in programming languages. We have seen a couple of examples of semantics for communications of and futures that can be considered as two possible basic semantics you can encounter for parallelism. We've designed ourselves a semantics for our mini-while language, and semantics that for the part that has threads and concurrent memory accesses. Then we designed another semantics for mini-while without concurrent accesses, but with futures and asynchronous function calls. And we designed a type system for this future version. And we've seen how we would prove property of this type system.